The dream of crossing the violent English Channel by underground tunnel was finally realized in 1989, with 50.5 kilometers, or 31 miles, Channel Tunnel becoming one of mankind's greatest engineering achievements. Every time a high-speed train barrels into a tunnel, it acts like a giant piston, pushing a wave of air ahead, squeezing the air tighter and tighter as it races through the confined space. In a 31-mile tunnel, that pressure can build up fast, reaching levels that would rattle passengers' ears, strain the train, and even threaten the tunnel's structure. To tame this invisible force, engineers designed a network of 194 piston relief ducts, each spaced about 250 meters apart along the tunnel's length. These openings, each measuring roughly 1.2 by 1.2 meters, let compressed air escape from the front of a passing train into the adjacent service tunnel, smoothing out the pressure wave before it could become dangerous. The analogy often used is a pressure cooker. If you don't vent excess pressure, things get risky. Here, the ducts act as release valves, protecting both people and infrastructure. But the system does more than just keep the air calm. In an emergency, massive fans, capable of moving up to 30,000 cubic meters per second, can reverse the flow, channeling smoke away from passengers and giving rescue teams a clear path. With this dual-purpose network, the tunnel's designers turned a potential hazard into a powerful safety feature, setting a new standard for underground rail travel. The fate of the entire Channel Tunnel project rested on a single question. Could engineers find a rock layer strong enough to hold back the sea, yet soft enough to carve a path for trains? More than 200 boreholes were drilled across the channel, each one extracting core samples that told a story millions of years old. The results pointed to a hidden band of chalk marl, a blend of limestone and clay, stretching from Kent to Calais, buried deep beneath the seabed. Lab tests revealed its secret. Water seeped through at a rate of less than 1/1,000,000th of a meter per second, and the rock could withstand pressures of 5 to 15 megapascals. These numbers meant the chalk marl would act like a natural barrier, resisting both collapse and flooding. Dr. Pierre Leroy, a leading French geologist, championed this layer after reviewing seismic surveys and borehole data. His team's findings shaped every decision that followed, from the tunnel's route to the design of the massive boring machines. Without this unique geological foundation, the dream of a tunnel beneath the sea would have remained just that, a dream. In the spring of 1802, as Europe paused between wars, a French mining engineer named Albert Mathieu Favier arrived in Paris with a plan that bordered on fantasy. He imagined a tunnel stretching beneath the English Channel, just wide enough for horse-drawn carriages to rattle through the darkness. His sketches showed a 20-kilometer passage, lit by flickering oil lamps and ventilated by chimneys that pierced the seabed. To break the journey, he proposed building an artificial island on the Varne sandbank, where travelers and workers could rest before pressing on to the opposite shore. Mathieu Favier's design called for brick and stone masonry, the same techniques used in city sewers and mines, but multiplied to a scale no one had ever attempted. The tunnel would pass beneath nearly 60 meters of water and silt, with nothing but hand tools and pumps to keep the sea at bay. Napoleon, ever hungry for grand gestures, listened to the proposal and saw a bold new route to Britain, one that could carry armies as easily as mail coaches. But within a year, war returned to Europe, and the dream dissolved. The oil lamps never flickered to life, yet the idea lingered, haunting engineers and politicians alike for generations to come. 11 tunnel boring machines, each a mechanical giant, advanced beneath the channel in a kind of synchronized ballet. These were not ordinary drills, but massive robotic caterpillars over 200 meters long, designed by Robbins in the United States and Kawasaki in Japan. Their cutter heads, 5.6 meters in diameter, chewed steadily through the chalk marl, while hydraulic arms pressed the machines forward against the tunnel face. As each section of rock was ground away, the TBM's conveyor belts whisked the debris backward, keeping the workspace clear for the next bite. Behind the cutter head, a ring erector swung into action. Precast concrete segments, each weighing several tons, were lifted, rotated, and slotted into place like the pieces of a colossal underground jigsaw. The machine's shield provided continuous support to the surrounding earth, preventing collapse before the lining could be installed. In the most challenging sections, the Earth Pressure Balance, EPB, system maintained just the right amount of force at the cutting face, holding back groundwater and stabilizing the chalk. Every advance was measured in meters, but every meter required a perfect sequence: cut, remove, line, and press on. With 11 machines working in parallel, the tunnel took shape not as one long bore, but as a series of carefully orchestrated steps, each one a small victory over the darkness and the unknown. Surveying a straight line beneath the sea without ever seeing from one end to the other pushed engineers to invent a new way of mapping underground. With GPS signals blocked by layers of earth and water, both the British and French teams turned to a shared coordinate grid, an invisible backbone that kept every calculation in sync. This grid began at coastal benchmarks, fixed points above ground in Folkestone and Sangatte, measured and remeasured to account for tides, continental drift, and even the curvature of the Earth. From these anchors, surveyors dropped plumb shafts deep into the ground, transferring the surface grid straight down to the tunnel level with sub-millimeter precision. The result was a triangulation network, a web of invisible lines and angles that guided every tunnel boring machine, every concrete segment, and every decision underground. To connect these reference points across the channel, electromagnetic distance measurement tools fired pulses of light along carefully measured baselines, achieving accuracy down to a few millimeters even over hundreds of meters. By building this Franco-British datum, engineers created a shared language of measurement, one that made it possible for two teams, separated by 31 miles of rock and water, to work as if they were side by side. Deep underground, every advance of the tunnel boring machine depended on a beam of light thinner than a pencil. A laser theodolite, mounted just behind the cutter head, projected its line down the tunnel, striking a series of photosensitive targets attached to the fresh concrete lining. These targets acted like checkpoints. If the beam hit dead center, the TBM was on course. But even a 10-millimeter drift, less than the width of a finger, triggered an alert. The operator would halt progress, swivel the cutter head, and realign before moving forward. Survey teams leapfrogged their stations every 250 meters, packing up each laser platform and setting it up further ahead, always keeping the line of sight clear and true. Each correction was logged and checked, feeding back into the central control system. Over the tunnel's 31 miles, this process repeated hundreds of times, narrowing the margin for error to almost nothing. By the time the two sides closed in on each other, the path had been steered with a level of precision that rivaled the most exacting laboratory experiments, a feat that made the final breakthrough possible. Before each advance, engineers sent slender probe drills up to 250 meters ahead of the tunnel face, searching for hidden fractures, water pockets, or unstable ground. If the probes revealed a threat, crews injected a low-viscosity grout, a watery cement mixture, into the rock to seal cracks and reinforce weak zones before the main excavation reached them. This process turned unpredictable ground into a stable shell, reducing the risk of sudden flooding or collapse. The central service tunnel always went first, acting as both a test run and a lifeline, giving teams a safe escape route and a head start on installing emergency systems. Layer by layer, these unseen defenses made it possible for the main tunnels to follow safely, even with the channel's weight pressing down from above. December 1st, 1990, deep under 40 meters of chalk and seabed, two men stood face to face in a cramped service tunnel, Graham Fagg from Britain and Philippe Cosette from France. Their handshake was more than ceremony. It was proof that years of calculations, laser-guided drilling, and relentless surveying had paid off. When engineers measured the alignment, the error was less than 5 centimeters across the entire 31-mile stretch, a margin tighter than anyone dared hope for at the start. For a moment, language barriers and national pride faded. The tunnel had united two countries in a single, unbroken line of concrete and steel, realized by the steady hands and sharp eyes of its builders. Every 8 kilometers, the tunnel widens into a maintenance zone, 6 in total, allowing crews to inspect and repair systems without stopping traffic. 2 full-width crossovers let trains switch tracks deep underground, adding flexibility and safety. To handle the constant heat from the earth and the trains, a chilled water loop keeps the air near 25 degrees Celsius. Some British tunnel boring machines remain buried, entombed in the chalk, silent witnesses to the tunnel's creation. Since January 1993, the ventilation and safety systems have kept the tunnel running, and on May 6, 1994, the first trains crossed beneath the sea. Every day, over 20 million passengers and freight tons cross beneath the channel. This is proof that bold engineering can connect nations, not just continents. As new infrastructure challenges emerge worldwide, the tunnel's legacy is not just what we built, but what we dare to build next. What would you engineer underground?